Hey guys, this is Sheri Baucom, and we are going to get started really soon because we have a lot to talk about. I'm going to launch a couple polls just to make sure that everyone is with me. Have you successfully implemented AI or machine learning? That's kind of grammatically incorrect because machine learning, which we'll talk about, is a subset of AI, but have you implemented this in your integrity program that you use on a regular basis? I did ask a version of this question in a survey that you guys, or they sent to registrants on Friday. And I wanted to remind you that if you're an AIP client and if you're using the assessment planning module on a regular basis, then you are using machine learning. So I just wanted to make sure that everyone was aware of that. And we're going to talk about that machine learning model later in the panel. So we have a few people that use AIP regularly, a lot of people that are exploring or piloting. So it seems like a lot of people in the audience have a healthy appetite for AI, which is exciting. So yeah, looks like the majority of you guys are exploring or piloting. So this is good to see. We are also seeing a lot of momentum and interest around how we can use the AI, machine learning, data science to help you guys manage your integrity. So obviously this panel is very timely. And I think we're going to go ahead and get started because we have so much to talk about. We have a lot of questions that you guys have submitted. So again, my name is Sheri Baucom. I'm the product marketing manager at Earth. Welcome to Earth Solutions. We are a software company. We make software that we have three different product lines: damage prevention, asset integrity, which is going to be the focus for this webinar, and also land and stakeholder management. This panel session focuses specifically on asset integrity software, but I did want to give a shout out to our damage prevention software, which also uses AI to figure out the riskiest 811 tickets that are coming in. So it helps pipeline operators prioritize which 811 ticket they might want to respond to or which one might lead to damage. So just wanted to highlight that there is AI being applied to the different product lines. But again, we're going to be focusing on asset integrity for pipelines, and that is our software that we created back in 2016. I say we, more so Jordan and Michael, and they'll obviously we'll be hearing from them later. But it started by applying machine learning to inline inspection data, and it originated out of the Microsoft Machine Learning Accelerator program. So it's pretty neat that we got our start using machine learning. So this is kind of our agenda. I just introduced Earth. We're going to introduce our asset integrity for pipeline software. And then I'm going to introduce our panelists. We're going to talk about challenges because there's a lot of challenges into applying AI and data science. The questions that have been submitted, you guys have a healthy amount of skepticism, so it's good to talk about what those challenges are. And then we're going to talk about how we apply data science, machine learning, and AI in pipeline integrity today in our software, and then also talk about future applications, and then again talk about trust and validation, because that was again a big topic that you guys were concerned about for obvious reasons. So our asset integrity for pipeline software, some of you guys use the software daily. Some of you are not familiar with it. We started out analyzing inline inspection data. So we have a bunch of modules concerning inline inspection management analysis, and that's where we use machine learning. We also have modules dedicated to internal corrosion, external corrosion risk, and geohazards. And a lot of that, obviously, we're getting a lot of different types of data, and we're getting a lot of you guys' integrity management data. Why is that important? So I don't just like to brag about how much data we have because I think it's cool. As you guys will learn in this panel, and what I've learned preparing for this panel is that the more data that you have, the better these models work, because these models, data science models or machine learning models, are based on integrity data. So the more data that you have, the more accurate these models are going to be. So our machine learning inline ingestion algorithm, for example, has seen 15,000 inline inspections and 500,000 miles of pipeline. So it's obviously significant, and it's not just from, say, one pipeline operator. That's from 20 plus different pipeline operators and 20 plus different inline inspection companies. So the amount of data that we have is significant. We're going to talk about that, and also making sure you have the volume of data, making sure you have the right type of data. Those will all be questions that we're going to be talking about. On that note, you guys have access to a question panel. So submit your questions at any point during the session. Feel free. If we don't get to it, it might be because I'm trying to keep a certain organization, but feel free to enter in questions at any point during the panel. We'll get to it. And a lot of you guys have submitted questions as you registered, and I've popped those into our agenda. So let's now do panel introductions. And I want to start with, I think, Jordan. Tell us who you are, your role at Earth, and in one sentence, if you can, how do you anticipate AI will change the pipeline integrity industry?
Well, thanks, Sheri. Yeah, I'm Jordan Dubuque, Chief Architect of Asset Integrity for Pipelines here at Earth. I work with our software engineering group, our data science team, on pretty much all things technical related to the AIP platform. As far as how I think about change from technologies like AI in the industry, it's hard to put that into one sentence, but just from a general sense, I think the trend with technology is around the opportunity to collect more data, to elevate and enrich that data, and then to apply more of that data into decision making and actions. And I think that AI is just going to continue that trend, and it's going to serve as one of the drivers for the next wave of advancement in all of those areas. The only other thing I would add is that I think it will be more of an assisting technology as opposed to something that replaces human expertise, but we're going to talk more about that.
Absolutely. Who wants to go next?
I can take it. Thanks, Sheri. Hey, everybody. I'm Noor. I'm the Director of Product Management at Earth here, mainly overlooking the product side of things when it comes to our Asset Integrity for Pipelines product line, which Sheri showed in one of her screenshots here too, encompassing ILI analysis, external internal corrosion, geohazard, and risk products. And I mainly work cross-functionally with everybody here on the panel today. For myself, from my conversations and understanding so far of where AI could benefit integrity management and pipeline industry, would really be using historical data for advanced predictive analytics. Can we find trends to make future decisions? So failure probabilities, or let's say using historical data to figure out what our next future dig plans would be. And so having AI to make proactive approach towards planning them efficiently would be one of the use cases that I see has come up quite a bit in supporting our operators.
I'm Michael Murray. I'm the lead data scientist for the AIP product. And I'd have to say that the long term, what I hope from AI and anticipate from AI is that we hope that they do a large fraction of all the time consuming day-to-day work that we have to do with. This is true, I think, not even just in integrity and with integrity engineers, but for my job and for software engineers too. Hopefully every time you're scrolling through an Excel file and looking and trying to keep in detail which one of these things, or every time you're scrolling across a pipeline and trying to figure out what anomalies you want to pick out and stuff, hopefully any kind of work where you're doing that is something that eventually AI will do for you and just bring the results to your attention for the sort of high level review, judgment call decision making that really is very difficult to either you wouldn't want to trust to a computer, or regulatory, you can't trust your computer. But in general, I think it's going to be a long time before those kinds of 20 years of experience decision-making calls are replaced by AI models. But definitely sorting through the data for all the ones where the call is a lot easier and bringing the more important ones to your attention, I think are hopefully what we see in the long term. I think we're a ways away from that kind of full performance enhancement for our job where every bit of menial task is being taken over by the models. So in the short term, we're looking more at specialized machine learning AI models that are specific to particular tasks. So maybe this is looking at cathodic protection survey data and saying, here are the particular areas with these combinations of data that require attention. It's much more specialized than just your whole job, but certainly specific models to specific tasks are I think the best promise for AI and ML in the current environment.
Megan?
Hi, I'm Megan Scudder. I'm our product manager of our corrosion line, so internal, external corrosion. And I'm going to give a really canned answer on this, but I really do think that ultimately it's going to make the pipeline industry a lot safer. I think if we take everything that Michael and Jordan and Noor said, and it's applying AI to a lot of this data that we already have, and that is really fragmented and not integrated together, and we're not extracting as much insights as we can about it. I think AI is going to help us to manage the large data load and also just the complexities of the threats to a pipeline. And ultimately, I think it's going to make the industry a lot safer, which I think is critical with the aging infrastructure that we have and not building as many new pipelines currently. So I think over time we'll see a reduction in releases and more targeted dig locations and just overall better management of the pipeline industry.
I like the theme of enhancing data and making us more efficient. I was thinking about this question. I'm not going to give a full answer, but I do think about how much data that we've maybe thrown away, or like old data, because it's not clean or it's not structured correctly, and how AI could assist us in analyzing that older data. So let's get to the meat of it. Jordan, not the easiest question to start with, but can you define AI and machine learning for us, kind of like context for this panel session?
Yeah, I can certainly try.
Yeah.
I've always felt like AI can be a bit of a tough thing to define. And I think for me, that's in part because, at least again, to me, the definition continues to evolve. Even since you mentioned, Sheri, we first got our start developing our platform quite a few years back now as part of Microsoft's AI and machine learning accelerator. Even since that time, I think the definition has changed a lot. But to start with the basics, AI it's really any technology that simulates what we think of as the core elements of like human intelligence. So things like learning and comprehension, reasoning and problem solving, decision making, creativity, and even more recently, things like autonomy, right? Systems that can effectively execute against those decisions more independently. Then I think of AI as like the toolbox and machine learning as one of the key tools or most powerful tools in the toolbox. Machine learning is a specific form of artificial intelligence where a computer program or a system, it isn't defined or like coded, manually like an algorithm that a software developer would write. Instead, a machine learning system is designed to learn or to define its behavior, typically based on providing it the questions and the answers together as a set. So how this might work is that we give the system what we call labeled data or training data, where for a given set of inputs, someone has already kind of figured out what is the desired answer or output from those inputs. And then machine learning is effectively working backwards from those inputs and outputs to derive a system, a set of criteria, some rules, you can kind of think of it, that given those inputs will produce the desired output as closely as possible. So Sheri, feel free to stop me there, but I can provide, maybe an example as well of, what this might look like.
Sure.
Yeah. Okay, so a real world example, a common one that we use to explain this is that you might have a set of email messages, and maybe a human user has manually flagged some of those emails as spam, with the remainder being, presumably legitimate emails. You could then train a machine learning model to effectively learn or back into that system for determining whether a new message that wasn't part of what was manually classified would be expected to be marked as a spam or not. So typically this is just about recognizing patterns in the data. And in some cases, it's patterns that may not even be known to any human or any expert that's trying to work on the same problem in a more conventional way. And this is something that modern computer systems, cloud scale computing resources with tons of processing power and memory can be very good at. Basically generating that model based on those patterns in the training data, which you can then apply to other data sets in the wild.
Which is, I think, so exciting. But then when people start referring to it as that black box, that's why you refer to it as the black box, because it creates rules, algorithms that you're not necessarily understanding what those rules or algorithms are. Is that correct? For a machine learning
Yeah,
model?
I mean, the nature of machine learning can make it difficult to understand why did you get a given answer, right?
Yeah.
And that's when we get into things like model explainability and some of those topics, for sure.
Validation, correct. Yeah. So let's move on to our second section. When you're talking about machine learning models, so they create these algorithms that you're not really aware of. You use what you call a training data set, and typically to validate them, you use a test data set, I assume. But what are some of the requirements to develop a machine learning model? Like what training data? Can you speak more to that?
Yeah, for sure. So the training data itself, maybe unsurprisingly, is a fairly big topic. But just generally, what you want are things like quantity. You want, a large volume of data available for training. Quality, obviously, is important in your training data. And also, I would point out diversity, that you want your training data to represent a wide range of different scenarios within the possibility space that you're trying to model. So a large volume, again, the more the better, of essentially confirmed data or like ground truth about whatever it is that you're trying to predict with your model. That's kind of like the fundamentals. And this is one area where I would say that Earth is somewhat uniquely positioned. Sheri, you mentioned it earlier, but more than 24 operators now on AIP, tens of thousands of pipeline inspections, hundreds of millions of anomalies. That's just on the pipeline inspection side. We also have hundreds of thousands of NDE records that are based on physical findings from the field and can be used as, sort of truth depending on what it is you're trying to predict with your model. We just don't think it's possible to train and to create the best models for the entire industry within any single pipeline operator and with only the data that's available to that one operator. Instead, our feeling is that looking at data across the entire industry is what's going to yield the most advanced, the most comprehensive models. Again, going back to those like quantity and diversity kind of components. And that's really core to our philosophy and our mission statement of better tools and ultimately better integrity decisions through the topic of shared learning. I'll pause there. We can talk about some practical examples of training data, or we can move on.
Yeah, well, I have so many thoughts. So this also comes up when I've been talking to Megan about the data science-driven internal corrosion susceptibility model, trying to create models on failure data, for example, where we don't really have a really nice repository of where failures happen, why they've happened. You can mine the PHMSA database, but that's something that that's a challenge, is figuring out like, okay, I want to know where all the internal corrosion failures happened and why. So I love that you're talking about that, like making sure that you have the volume of data. Also want to move on and talk about the like the quality of the data. So Michael, to that point, what are the biggest hurdles around data quality, structure, and consistency that we need to overcome when we are fully leveraging AI or data science models, however you want to take that?
Yeah, sure. So I would also keep going a little bit on the quantity there. So
Yeah.
I mean, you can mine the PHMSA data set, right? The ultimate sort of labeled data for training any model is like, here's all these releases. Let's predict where those releases are. But thankfully, there are not that many releases, like in the scheme of things, right? There's tens of millions of anomalies in our
yeah, exactly.
There's like tens of millions of anomalies in our database, and just a tiny fraction of that end up being releases, which is obviously good. We don't want lots more of that kind of training data, but now you're talking about what's second best, right? And now it's field measurements, places that have gotten a repair, places that are in the judgment of integrity engineers are anomalies of concern. I mean, that usually leads to a repair record as the actual truth point there. But then it always seems like lots of data. Tens of millions of anomalies is a very big number. But anytime you're starting to do any kind of study, you have to start cutting that number down. So all of the anomalies that are just at threshold, barely above detection, those things are usually not very useful, right? They're not that critical. It might even just be noise. So that's a big cut of there. You need to filter down by the anomalies that actually have repairs and field measurements associated with them to generate your truth data. Usually you're not just looking at any, to the point I made earlier, we're usually looking at some kind of a specialized model, and you're looking at either like only corrosion data or only crack data, or only specific types of corrosion or specific types of crack in relation to their position on the pipe or other properties. And that's another big factor that's cutting down on this thing. Once you keep adding these in and looking for specific failure modes and maybe specific interactions between anomalies, 10 million is actually not that big anymore. It's like you cut it down by, factors of 1 million, and now you're looking at 10 anomalies, which is not a huge statistical sample. So it's really hard to overstate like how much just more data and accumulating all the data in one place to search for those needles is important. I'd say that in terms of quality, I think the biggest challenge is not necessarily exactly like data quality. It's not like some data is bad, some data is good, although that is, of course, true and things get better over time. But another big challenge is just the different definitions across operators, across time, even within one operator, the anomaly, the way the particular anomalies are defined, or interaction rules between anomalies change even from run to run, parameters that are used for different engineering calculations, or tolerance values and how those are calculated. Those kinds of sort of like different definitions and different standards across operators and across time change. And you want to make sure that when you're training a model and treating some variable as like, okay, this is, an anomaly that's interacting with the seam weld. Like, well, that definition has a lot of nuance to it, of course, and it depends on a lot of different factors and has changed over time and changed by the tool technology and everything. And so when you're actually like parsing through the data and trying to figure out how should I include this data point or not, you have to sometimes take those things into consideration. And so I think bringing everything into a schema where those definitions are sort of standardized, and we can look at we can sort of have a little bit more trust that when you pull from this database table, this is anomalies that are interesting from this perspective at this category. Like that kind of regularization and schematization is incredibly helpful for being able to quickly iterate on machine learning models. Because ideally, most machine learning models don't work. You try something, you see if it's got some signal there, it ends up not working. You want to learn that quickly, and you move on to the next thing to see if it's going to find something else somewhere else. And you don't want to spend all your time in the data engineering and data wrangling, which just from experience is what 90% of the effort on every machine learning project is data wrangling and gathering and
Structuring.
testing and making sure you understand and structuring.
Yeah.
Exactly. So you want to cut that down as much as you can, and regularization and putting everything in a database and standardizing definitions, or at least understanding the different interpretations of definitions is incredibly important for that.
And to that point, I think a related question. I like this question because it's definitely something I would ask. So if I was a pipeline operator and I had one pipeline and I could upload everything about that pipeline, so pipeline data, coding, wall thickness, inline inspection data, external corrosion surveys, and I just throw that into ChatGPT, what would happen? Like, what would ChatGPT tell me? Could I query that data for meaningful information, talk to that a little bit more? And I think you kind of already touched on it. It's, I'll just let you answer that.
Yeah, sure. So I think the first point is that actually even just a single ILI tally, you can't actually fit it in an LLM. They have token limits for their contexts that are sort of in the million token range, and an ILI file has not a million different anomalies, but each of those anomalies has a lot of data attached to them, and so it probably doesn't fit in there. But then there's also a lot of studies that show that the more data, the more you use up that context limit, the less the LLMs keep track of individual data points. They do these cool studies where they insert a needle into the text and see if the LLM can recall that needle, and you try to add more context data or shift where it is in the context, and it gets better and worse depending on the situation. It's hard to be 100% definitive here. These things are changing very rapidly, and in a year, this answer could look silly because it handles it perfectly, right? But it also could not. It's hard to be sure exactly what's going to happen in the future. But as of now, I think that my experience with trying to load sort of tabular or like structured kind of physical data about the physical world, which is what a ILI tally is, into these LLMs is that they're not very reliable about even just sort of extracting and describing the information to you. Far from what you would need for actual, I think, useful information from a sort of integrity analysis perspective. Like, you want it to be able to understand your IMP, to understand all of the regulatory conditions in order to actually like produce something out of this thing, which is even more context needed. That I fully believe is something that could be built in the future, but I think currently my experiences in trying to do that have been sort of not encouraging from looking at what actually comes out of the LLMs. Although if anybody has done this and seen better results, I'm very happy to see the actual example where it happens, because that's something that would be incredibly helpful and scalable, right?
So you can't just throw all your unstructured data in there all at once and hope for that it's going to come up with something that makes sense, basically.
I mean, unless somebody's got their magic wizard for prompt engineering. Also, the other thing is that how you ask the question also matters a lot in some contexts. Yeah. So it could be that there's sorcery out there to be discovered.
Yeah, well, and I think it's really important. I feel like a light bulb moment for me is like the LLM not understanding the context. So the LLM not understanding, like, you're putting all these like Excel tables of numbers and text, and for that talks about inline inspection results or corrosion, like CP data. Like, it doesn't understand that this is describing a physical asset. So alignment, like how those values line up, like a CP point to an anomaly, it doesn't understand. It can't infer alignment, basically. Like, it doesn't understand that. But that's something that we would have to, like a model would have to do. Like, and that lends to itself with making sure the data is structured, so that
I think from whole cloth, like it understanding the concept of aligning tally over tally, and then even more broadly, like aligning to GIS, aligning to like close interval survey data, like getting those data sets aligning to any sort of other data set you'd want to put on the same sort of linear space. I think that understanding that for whole cloth is pretty far away. On the other hand, that's also the kind of thing where you really benefit from, like, at least in our experience, is that it really benefits from a lot of rules-based algorithms prepping the data and pulling together, the basic structure of how you would line up data together. And then I think there's still quite a bit of opportunity there for the trickier individual problems within that, applying some small ML model to solve, the hairiest parts of alignment or anything like that. But I think it's expecting a lot to see an LLM or see ChatGPT or something like that to pull those kinds of ideas and concepts and algorithms out from whole cloth.
Got it. Jordan, to the last question, anything to add there from a data architecture standpoint when you're creating an AI model, specifically when you're feeding the model the data that it needs, something that we haven't covered with Michael's response before we move on?
Yeah, I would just kind of reiterate some of what Michael said. And, I know everyone on the call is likely well aware, but data in our industry, it really comes in a wide variety of formats, unstructured and semi-structured data sets that, again, typically need to be processed or interpreted first in order to develop models or to feed into existing models. And that's why, as you discussed earlier, one of the first areas that we apply machine learning is on the ingestion and normalization of data, like inline inspection, into like a standard schema, a standard taxonomy. And that standardization process is fundamental to pretty much everything you would want to do downstream. The only other thing I would say on top of that is that the next sort of immediate challenge is really around data integration. Sheri, you talked about it in terms of a challenge for an LLM to understand how do these data sets link together. But you want to be able to look at data holistically, combining and aligning data from what might be relatively independent sources. So common examples, ILI and GIS centerline, or ILI and CP survey that you mentioned. This is where you really need some kind of additional tools and algorithms and other methods that can align and match up data, potentially using like distinctive patterns similar to what we do with the anomaly box matching, for example. And it's important to design those systems with scalability in mind so that it can handle the large volume of data and really make accessible all of the historical data.
We're going to now move on to what we can do. But I think it was important to talk about what are the challenges, because you can't just wave your wand and throw your data into AI and hope for the best, right? So I want to get a little more optimistic here and talk about like what are we doing currently and what do we think is possible in the future. So I'm going to go back to you, Michael. You're in the hot seat still. Talk about data science, because obviously I know that the buzzwords are AI and machine learning, but like data science is really important. And I think you mentioned like 90% of this is data science and like wrangling the data. So can you talk about like how data science fits into all this and how it relates to machine learning and AI?
Yeah, sure. I think that the terms get a little bit confused, and trying to like make hard and concrete distinctions between them is tough. I think probably because at least let's take AI for example. It has, at least as far as I can tell, at least 3 different meanings. There's kind of the keyword of the moment, or like the buzzword of the moment. A long time ago, this was big data. It evolved into everybody wanted to say they're doing data science. Everybody wanted to say, a few years later, they're doing machine learning, and then it's deep learning, and then it's reinforcement learning. Now that current word is AI, right? So everybody wants to be saying they're doing AI. And as a consequence of that, a lot of stuff gets thrown in that bucket just to, say, yeah, we're doing AI because we're doing these things, right? But then, of course, it's also a technical definition of an area of research that's very distinct from all of the stuff that came before it. It's a replica or approximation of the way humans make decisions with, using neural networks and that same idea. That's been a subject of research that goes back decades, to the 70s. People were first trying to do these kinds of the same sort of projects. It just didn't have the computing power. And then, of course, there's also the level of AI that's I don't want to say purely, but it's like largely a fundraising and marketing term, where it's like if you can say you're doing an AI firm, then you get more VC funding, right? So all of those things are definitions of AI, and all of them are used in different contexts, and so you kind of have to be a little bit discriminating about how you think of them. But it is a real different field of research involving this kind of, obviously LLMs are different than anything that's come before it, and the sort of deep machine learning models that are solving chess and Go and things like that are obviously different from the algorithms things are being used 10, 15 years ago. So I guess I would prefer I always prefer to think about the sort of technical definition that's most useful in that context. And then machine learning is kind of a specific style of algorithm, which is like it's a tool, right? It's not necessarily I always kind of get a little annoyed when it's like, we have to use machine learning to solve this problem. You want to make sure it's the right tool for the job, just like any kind of algorithm. Thankfully, it's very applicable for a lot of different scenarios. But machine learning is anything where you're taking the outputs that you want to see as the result, and then changing the way the algorithm works in order to produce those outputs. So training on the outputs, and in a way that's not necessarily crafting the rules yourself, but allowing the algorithm to figure out the rules on its own in order to replicate those outputs as well as it can. I would say data science encompasses all of those things and more. Anything, I'd say the data scientist as a title, given that it's my title, is probably the least descriptive thing to tell what a person actually does day to day. If you talk to somebody at a cocktail party, in our job, it's it's algorithms, it's ML, it's researching where can these LLMs be most effective in a context like AIP. But data science encompasses all of that, even rules-based algorithms, even just like implementing engineering calculations in a way that's computationally efficient. I'd say that all of those things fall under the broad umbrella of data science. But of course, the definitions that's my definition. I don't want to claim that it's necessarily definitive.
Well, it's important to know that there's like a good amount of overlap. I think that it was also like one thing that helped me, I think, is understanding that both of them, like machine learning, you can create a machine learning algorithm that's also based on data. You can also create data science driven algorithms that are based on data. It's just machine learning. Those models can update themselves, which is why they're referred to as like a black box. And then they also, for some reason, we use the term model, I think, a lot more for that than data science algorithm versus machine learning model. I don't know why we do that. Maybe that's just semantics, but that's just kind of how I organize it in my head.
A black box nature, you want to like put a box around that and say this is the thing where we put the data in and something comes out. So model is the word we use for that.
Yeah. So to add to that, what does machine learning look like on a day-to-day basis? I do want you to briefly talk about the machine learning ingestion algorithm. I have a little visual that I pulled from another slide. And then the data imputation project, because I think that highlights really well, like how machine learning works for pattern recognition. So
yeah, sure. So I think that the challenge with any machine learning model is you want to be able to find a problem that's like tractable with it. So you need to find something where you have good, well, it depends on the types, styles of machine learning, but for the examples we'll talk about here, you need to find something where you have good labeled data. You can actually try to reproduce the outputs that you want here. There are ways to do sort of machine learning that aren't, that's, separating your data into categories, even though the model doesn't know what those categories actually are. That doesn't require labeling exactly. But I think from our perspective, the most useful ones end up being this kind of labeled classification or prediction models. So the classification algorithm that's the sort of core of ingesting data or ILI data, especially into AIP, is taking all of the different ways that things are labeled and called and categorized in ILI files and turning those into this regularized schema that I was talking about before. You want to know, like, what are all the different ways girth welds are called? Turns out there's thousands of different ways girth welds are called in ILIs, sometimes without even any words at all or any text. They're just a line that doesn't have anything else on it. There's a lot of different ways you can spell machine learning or misspell machine learning, or not machine learning, sorry, metal loss. Get my ML confused. There's a lot of different ways that any one of these like categories can get labeled or called out in an ILI file. And so the core part of our data ingestion is to make sure that we're trying to bin those in buckets that are useful for downstream analysis. So it's still, the categories are context dependent. When, it's a girth weld, it's metal loss, it's dent, those things are pretty clear. When you get to more sort of obscure like calls in ILI tallies, then it could be, much more context dependent on exactly what something needs to be called. And then of course you can't ever just walk away from these things and have them produce answers for you. You still need to be constantly thinking about and reevaluating the model and training it. So training on the ingestion model happens continuously. Every time we bring in new data, especially from new clients or new customers, where we're seeing sort of like, what's the word I'm looking for? We're seeing like the way, like particular ways of calling things that we haven't seen before. Conventions, that's what I was trying to say, like different conventions for the first time. Then we'll always see a new way of seeing a new spelling or way of phrasing some particular feature or property. And so we have to constantly looking for new data. And when we see new, like novel inputs, then we have to be training and making sure that we're getting those to be the right outputs. And then from, then on into the future, those outputs will be mapping correctly to the right, those inputs will be mapping correctly to the right outputs. And in that sense, over long periods of time, we've gotten to the point where, the vast majority of column names and row names and everything get classified to be without having to do any intervention and without having to do any retraining. But obviously, it's always possible to find new things, and retraining and constant updating of models is always necessary, no matter what kind of machine learning problem you're doing. So beyond ingestion, we're always looking for contexts in which we can do a better job than, or at least a more efficient or a quicker job of categorizing or classifying or predicting different outputs. One project we were working on in the sort of recent past is still working on is data imputation ideas. If you have missing properties in a pipeline, like you don't know the coding type, or you're unsure of the coding type, or coding conditions, or even not having the records for the install years, can we build a model that is? We have built models that try to predict the actual pipe properties just based on how similar is this joint of pipe to joints of pipe all the rest of the systems that you operate. So if you have similar install years, similar wall thicknesses, similar pipelines and other properties, then maybe the coding type is similar to the ones that were installed in the same way. And that model, again, you can train it based on, we do know what the properties are for a large fraction of the joints of pipe in the ground, and so we can pretend like we don't know. We can use that as our labels. We can use this to predict, to train the models in order to be able to predict the unknown quantities. And then that that actually building the model and doing that kind of analysis is not that time consuming. Again, data manipulation is a large fraction of the like effort that goes into it. But in this particular case, a lot of the effort is also thinking about the sort of real world physical problems that you're dealing with. With data imputation, you always worry that, you know, the data that's missing is not missing because of random hard disk failures. It's missing because the records weren't recorded correctly, or maybe the records were recorded incorrectly in a way that really affects, like, it's not the same data that was missing as the data that you're training on, and therefore your model's not going to be as accurate as you think. So thinking about those issues and how to minimize those effects is the you know, most amount of effort and, I guess, brain power that needs to go into how to use these models, rather than being able to just apply them blindly.
So we need to move on, but I think it's interesting because this one I feel like was kind of like controversial when you talked about this at User Summit, and controversial in the way that when you're talking about inputting missing data, there is some regulatory concerns with, like, you know, if you input a missing wall thickness, for example, is that something that we can talk to PHMSA about and defend? So and we've actually gotten like 3 questions while you were talking about that. TVC concerns around data imputation. So TVC is traceable, verifiable. And then data imputation use case. So let's hold off on those questions. We're going to talk about trust. I want a trust and validation of the models. I want Noor and Megan to be able to speak on what they're currently doing with machine learning, data science, and AI. So Megan, do you want to speak really quickly on how the data science driven internal corrosion susceptibility model and how that works, how that's put together?
Yeah, and after listening to Michael, I'm wondering, should I be calling this a data science algorithm or a data science model? Now I don't know. Yeah, so really quickly, we've developed an internal corrosion susceptibility model. So we've been able to take everything that's done upstream. So what Michael was talking about on really cleaning that data up and categorizing it in a way that's meaningful, that we can then build a model or an algorithm based off of that. So we've taken the ILI results for internal corrosion, and we're extracting as much data as we can out of that. We're looking beyond just what is the anomaly dimension and classification, but what is happening with that anomaly in terms of growth, what's happening around that anomaly with other anomalies. So what are they doing? How is that impacting a current anomaly? We're looking at where is it on the orientation on the pipeline? Is it in a low spot? So really taking everything that we can out of the ILI results and then comparing that to where there's known failures. So that goes back to earlier conversations on, mining the PHMSA database and really trying to provide meaningful results back to operators in terms of this is where you are highly susceptible to a release on your pipeline. So we use data science to take all those parameters that I discussed from your ILI results to apply weightings to them to say this combination of this weight of these parameters would have flagged this known release location. And so we use that training data to determine those weights, and then we will rerun this model on pipelines where there may not be releases, or we've done it for a client where they have releases, they don't tell us where the releases are, and we have to try to match those locations. So, it's a really specific model that we've been building and using our data on, but we've seen really good results from it, and we're hoping to work with customers more on understanding, like Michael mentioned, beyond just release data, but maybe near misses or information that this was a really critical anomaly and things like that, so we can continue to grow and develop the model.
Yes, thank you, Megan. And I'm going to not ask a follow-up question because we need to get going to talking about future. And Noor, I'm going to have you do a 2-part. What are you seeing? Because you've been doing voice of customer interviews with clients on like how they're using AI now and what their appetite is. So can you speak to what you're seeing now, and then maybe just hit on what we're looking in the future to do with the software?
Yeah, for sure. I can summarize that here, Sheri. So we took recently an approach in the past months to really connect with our users and operators today who are using AIP to understand how they are leveraging generative AI in specific, which is a subset of all the AI functions we could leverage in the product. and really how they are approaching large language models in their day-to-day workflows when it comes to pipeline integrity. And we observed that they're really in a early to mid-stage adoption of these different tools that are available out in the market, which could be Copilot, ChatGPT, Grok. They could be using it as a personal workflow, or really embedding it in an organization on their business applications overall across different departments. This could be as basic a use case of creating schedules or uploading an ILI data to capture insights, or researching for, let's say, PIMSA regulations, or creating executive summaries. We had these conversations to understand kind of the use cases that users were looking for, so we could work towards a solution within our AIP product. We understand that use cases differ depending upon who is leveraging AIP. So largely you could put it towards two different subsets. You have your management persona, who is looking for overarching use cases of what's the general health of my asset, and understanding metrics that are more overall than specific. But then you have your integrity engineers who are really looking to understand things like, what are my anomalies due in the next 60 days? What were the dig plans that I did in the past 5 years, and how can I project towards the next ones? And so based upon that information, then we've gone ahead and validated 3 base use cases, which form the basis of our upcoming generative AI solution. Namely, this allows users to, if I were to define those 3 base cases, an interface that's more intuitive and allows user to interact with our product, to ask questions on the basis of the data that we host in AIP today. Users will have the ability to use natural language to create prompts, much like they do in Copilot or other applications, and automated reporting and executive summaries. Alongside this, we are exposing supplemental materials to help support our operators in onboarding new users into the platform. So things like our user guides and frequently asked questions. And we're really building this towards making sure that users can intelligently really query the data that it exists in our product today. As to where we stand today, we have built a proof of concept based upon these 3 base cases and other principles that I have just shared. We also have defined our user interface and what that would look like, and design principles for it. We're just working now towards a development plan to incorporate it as a part of our 2026 and onwards roadmap. But that's kind of the summary of what we've heard today, and how we have leveraged that feedback to incorporate into our roadmap.
I love that rapid fire, Noor. Okay, because we gotta get into our rapid fire questions, because I think we've had like 10 plus questions as you guys were talking. So we're gonna run through them, and a lot of the questions have to do with validation, trust, and data, which is, again, I feel like the themes of this. So we're gonna start with Josh's question. Michael, what is accurate data? Michael reiterated many times that you need accurate data to train these models. ILI and NDE data are not necessarily accurate, right? There's tolerances. So it is industry accepted that even NDE truth data is not always truth. How do you train models with the possibility that none of the data you're collecting is accurate or truth? Is that something that you
sure.
answer succinctly?
Yeah, I sorry if I said this in a way that implied that. I don't think that you need accurate data to train models. Obviously, you can't in this context, right? ILI tool tolerances are quite large. Even field measure data has some tolerance attached to it and variance to it. So you need to work with you need to have models that are robust against that, and that means that you need to be evaluating the performance and predictions and training based on kind of statistical ensembles of measurements in order to reduce that variance. That's the 2-sentence answer, I guess, Sheri.
Okay, great. I want to move to because we've gotten like 3 trust questions from pre-registrants. Real world pipeline data is somewhere between, let me move to the section here, between low, no trust and high quality verified pipeline data. How do we use AI, or can we use AI for QA/QCing the data? And I also think someone also asked about, like, is the data, or can AI be used for enhancing, or is it going to be used for automating? I think those questions are related. Who wants to take that?
I guess I can. So in terms of QA/QC, I think that kind of outlier detection and sort of statistical analysis for looking for. I mean, obviously there's procedures, there's whole, workflows and everything for how to do this in the pipeline industry. But in terms of finding things that wouldn't normally that would fall through the cracks in those workflows, I think AI has some promise to do that. I don't have a lot of experience with actually doing specific tests for those things, but it's certainly open to ideas there if somebody has them. I think that in terms of the trust question, that's part of why I said at the beginning of this that I think we're a long ways away from throwing your data into a model and getting answers out. It's the judgment and intuition and knowledge coming from people who are experienced in this industry and engineers and stuff at looking at the data and making those calls it's very hard to imagine that being replicated in a model in the short term. And so I think we're definitely in the case where it's the models can maybe bring to your attention things you wouldn't necessarily have taken a second glance at before, and then all of the just making it an engineer more efficient at being able to bring stuff to the table, use all your sort of high level thinking and all of the I guess all of the judgment calls and stuff that are hard to replicate in the model, and make sure that's what you're spending your time on. I think so enhance over replace is my answer there.
But I think, and again, a lot of people so there were some questions and they were pretty broad. They were asking well, how accurate is the model? First off, I didn't know what model they were talking about, but the machine learning data imputation project, I think you said it was 99.7% accurate on identifying the wall thickness. But then people are thinking, well, what about that 0.3% that it's not accurate? And so there's obviously going to be concerns around that. And I'm glad that pipeline operators are thinking about that. That is their perspective, though, is how do I defend myself against PHMSA when I use AI for these decisions? I don't know if we necessarily have the answers to that, but obviously there are ways to test the models to discern whether they're accurate. And then I know that we've talked about LLMs, when they generate answers, they source, they identify what their source is, right? So you're how many anomalies are high risk if if we created a chatbot that you could ask that? Well, it's going to give you the answer, and then you can make it so it tells you where the source of that data or that answer came from, right?
Yeah, I think that's not something that comes out of the box with them. That takes a lot of engineering to make them so that they accurately source their results. But there's examples of that work. It's a non-trivial task to get that, so you actually get useful link backs to the things that are real and not made up. But it is true that could be a useful, if they can actually do the analysis, right? If they can pull out the numbers that they're supposed to be using in these calculations and so forth, and not make mistakes or hallucinate.
Someone asked, can AI testify for you? I don't know if we're gonna be there.
You gotta have a panel of lawyers on the next one, Sheri.
Yeah, maybe. I want to get back to a client submitted question. It's a little bit open-ended, but I think it leads to a good the future of AI question. This is a pre-submitted question from someone that registered. Can we teach AI by having it watch and listen to how we do things rather than develop training materials? And I know, Jordan, there's a similar question. Someone mentioned agentic AI, which I just learned what that is yesterday. Does anyone want to tackle this question?
Yeah, I guess my response to this one, Sheri, would be that, AI, again, really broad umbrella term. And within that toolbox, there's just a wide variety of tools. We've talked a lot about LLMs being one of the more recent sort of innovations and areas of focus in this space. And just the breadth of tools provides a breadth of capability. So when I think about this question, these AI tools do have a growing ability to ingest more types of data, right? They express this in, they call it multimodal capabilities, the ability to take in audio recordings and transcribe it, to take in text in different formats, maybe even imagery, et cetera, and to process that into, products essentially of all of that input data. So I don't know that we're there today that we can say, well, just create a bot that listens in on our meetings, and then by the end of enough meetings, it is a expert on the topic of pipeline integrity. But I do see lots of advancement in terms of the ability for these tools to consume data in different ways and a wider variety of data.
Maybe I can mention, since we haven't really said it, I do think one of the big promises of LLMs, and I mean AI in general, in terms of how to analyze data and look at it, is from once you have a structured database of, I mean, very vastly complicated database, asking questions about, hey, how can I build a study, or how can I build a report that incorporates this data and this data, and having it generate sort of the scaffolding of, here's what a study would look like, here's the SQL code that goes behind the scenes and looks it up, and then say, okay, starting from here, let's double check, let's validate, let's make sure these quantities are actually things we want, and then having that vastly improved productivity in terms of just quickly getting out reports and quickly getting out code and structured data from very large structured databases is, I think, highly promising, and it's definitely an area we're pushing for in terms of how you can interact in AIP.
Can AI be used to prepare for audits by asking questions about things like current pipeline conditions or draft threat assessment reports to present the current state of the pipeline?
Yeah, I mean, I think that it's going to be hard for that to be, especially in that context, right? For it to be like something you want to trust, you definitely need to validate. But in terms of, look at this database, produce this kind of report with this kind of information into it, even in sort of natural language description, I think that is something that is very plausible.
The future is bright for AI. Well, thank you guys for joining us. I have learned a lot preparing for this panel session. I hope you guys learned a lot. I'm sorry that we did not get to a lot of you guys' questions. There's about 5 or 6 that I would like to respond to, and I will follow up with everyone that entered questions. But yeah, thank you guys for joining us. Take care.